let's talk about slow crack growth. Okay, this should be a shorter presentation. Okay, okay. So we already discussed about theoretical background concerning crack propagation in brittle solids. So I won't go into much details in this first part. My idea is to describe slow crack growth at the nanoscale, let's say at the atomic scale. And what is the mechanism responsible for slow crack growth? Why slow crack growth can occur? And this is due to a stress-assisted corrosion at the crack tip. And we will also show the effect of glassy phase on slow crack growth. And then we will turn towards slow crack growth at the micro scale, the effect of crack bridging on slow crack growth. So we have seen the effect of bridging on toughness. We will see the effect of crack bridging on slow crack growth, effect of phase transformation on slow crack growth, and also residual stresses. And I will apply these concepts to the case of ZTA composites, so zirconia, tough, and alumina composites, and nano-composites. And let's say from the BioCare approach, so the first European project we had on that aspect, towards the nanocare approach. So we already talked about that. What is important is we said that for a given applied stress, a flow will propagate at a given rate if its size is above a certain value. And so what is important also to remind is that what is resisting to crack propagation is really the creation of new surfaces. So you have to create two surfaces, and so the resistance of a ceramic in front of crack propagation is especially due to creation of two new surfaces. So gamma is the surface, is the energy necessary to create two separate surfaces. We also saw this local approach. We said that around the defect there are large stresses, and so they were well described by the stress intensity factor K1. And we said previously, Gilbert and myself, that when K1 reached a critical value, K1C, so there is crack propagation. And now this is not an error from my part. I said propagation will occur if K1 is above a certain K1 zero value. And this K1 zero value is related to the energy necessary to the fracture of the ceramic bond. So imagine this is a crack, large stresses at the crack tip. When these stresses reach a critical value, a certain value, then the crack propagates. Of course, this value is linked directly to the energy of the bonds, of the atomic bonds. So when you reach a sufficient stresses at the crack tip, then you have crack propagation. And from now, we said the crack velocity is null until you reach a given threshold. And if you reach this threshold, rapidly the crack will grow at a really high speed. So if we completely forget any dissipative mechanism, we would say, okay, here is the crack velocity versus K1. For low K1, below this K1 zero, so this is the atomic bond related energy, there is no crack propagation. And so when we reach this value, so rapidly, you have large crack velocities. And so the crack velocities should be on the order of the velocity of the sound. So 10,000 meters per second. So large, very large crack velocities. But, so if there is no dissipative mechanism, nothing than only creation of two surfaces, K10 and K1C are the same. So K10 is the threshold below which no propagation occurs. We said before idly crack healing. And K1C is the stress intensity factor for which a crack propagates at the sound velocity. It's about the same. There is no dissipative mechanism. But this is the case of a pure elastic solid. For a pure elastic solid, K10 and K1C should be the same. In real materials, there is always a certain amount of dissipation. I take this image, simple image of a ball. I take a small ball and I drop it like that. It will take a given rate, a given speed, which is a function of the dissipative mechanisms. So if I drop the ball in air, it will take, after a moment, a constant velocity. If I drop the ball inside an oil, for example, it will take another velocity, and lower velocity. So the velocity of the ball I dropped is a function of the dissipation. And we know from Gilbert's presentation that there is a process zone around the crack tip. So there is always a certain amount of dissipation at the crack tip, even low in ceramics. So if we have a dissipation, we can separate the threshold below which crack propagation occurs and the toughness, low crack rate, typically 0 crack rate, and large crack rate for K1C. And the larger the dissipation, the larger the difference between K10 and K1C. So that's the first point. We can imagine that we can have a difference between K10 and K1C first. Second, we can imagine to measure finite crack velocities. So in terms of ceramics, in terms of crack propagation, what is the effect of the environment? Typically, I will talk about water on crack propagation. On our global approach of crack propagation, we can say that water, presence of water, will decrease the surface energy. Remind you that I said the resistance to crack propagation is directly related to the creation of new surface energy. So this means in the presence of water, you should decrease the resistance of the ceramic, since you can decrease the surface energy. So the resistance of a ceramic will be given by the environment. And we know that water adsorption on surface is important. So water can have an effect on the surface energy. That's the global approach. Clearly, water should have an effect on crack propagation. At the atomic scale, the nanoscale level, we can talk about stress-assisted corrosion by water. Imagine a zirconia bond. I took the example of zirconia. I could have taken another example. So this is a zirconia bond, and we are at the crack tip. So this bond is highly stressed, since we are at the crack tip. And imagine there is a water molecules arriving at the crack tip. Zirconia bonds are ionic, highly ionic bonds. So this means zirconia is charged positively, oxygen is charged negatively. And you have a water molecules like that. Hydrogen, oxygen is charged negatively, hydrogen positively. You can create quite easily a ZR-OH bond here and a ZR-OH bond here. So in the presence of water, you can have a breakage of the bond at lower stresses than without any water at all. So you have a kind of stress-assisted corrosion, since water plays a role on the crack propagation, and it happens in the presence of high stresses at the crack tip. So water has a key role on crack propagation in ceramics. And by water, we mean a ceramic piece in air. There is always some water in air, as you know. Important also for implants in the body. There is also some water in the body fluid. So this is important in practice. At the surface of ceramics, there is always, in practical terms, some water. And water decreases the stress intensity factor necessary for crack propagation. And we have now some atomic scale simulations. So this is a work done by Yip 4 years ago already. And they showed that it was possible to simulate the effect of water on crack propagation. Here is silica, or a model of a silica here, and then water arriving here, and so these bonds are highly stressed, and then you can see that water can absorb at the surface of this silica, and then help to break the bonds. And what was important from their work is that they compare the stress necessary for crack propagation without any water, so breakage of these bonds without any water, and breakage of these bonds with water. And they found that bond breakage in the presence of water can occur for a stress about 40% of that necessary without water. This means with water, without water, you need, for example, 100 megapascal. With water, you only need 40 megapascal to have this bond breakage. So that's a huge effect of water for crack propagation. And it should occur in this simulation, it should occur also at the crack tip. So they also shown that you need definitely some stresses for crack propagation. So they also confirm what's important parameter, which is confirmation of a threshold K10 below which no crack propagation is expected at all. So below a certain load value at the crack tip, there is no crack propagation at all. Above this value, a crack can grow at a given rate. So here is an example of a V versus K1 curve of one ceramic, which is used for implants, for example. This is for zirconia. Here is the crack rate versus applied stress intensity factor. So remind you that K1 is the stresses at the crack tip, and here is crack velocity. So first, let's go towards results obtained without any water, so under vacuum, and in oil. Here is this diagram. So first, even under vacuum, there is a difference between K1C, which means fast fracture, and K10 below which the crack velocity tends to 0. So even without any water, there is a difference between K10, 0 crack rate, and K1C, high crack rate. What is important is the effect of water. So let's take the results in air. 3 propagation stage, 1, 2, 3 here, and a tendency toward the threshold below a certain K1 which is applied. So below this 3.5 megapascal square meter, the crack velocity is 0. Just above, the crack velocity is no more 0. And it's quite a lot for me. 10 to the power minus 9 meter per second. You think it's low, 1 nanometer per second. But this means 3.6 microns per hour. This means dozens of microns per day. This means at the end, after some days or weeks, breakage of the ceramic part. So no breakage at all, delayed failure just above this threshold. And there is a big difference between this threshold value and the toughness. Toughness means high crack rate, failure at high rate, 6 megapascal square meter. In air, the threshold is about 3.5 megapascal square meter. In water now, these are these red triangles. You can see an increase of the crack rate. So the higher the water amount, the larger the crack rate, and the lower threshold, lower surface energy. Increase in the temperature. This is a thermally activated reaction between water and the ceramic bond. There is an increase of the crack velocity. And you can see that in practical terms for zirconia, the difference between K1C and the threshold in water is about 50%. K10 is about 50% of the toughness. So that's not so different from the atomic scale simulations we have shown before. So there is, and it's important, really a threshold stress intensity factor below which we know that we should expect no crack propagation at all. And for implants, for example, for real parts that should stay for a long time without any delayed failure, you must be below this threshold, below which no crack growth definitely occurs. So do we have the same tendency for whole ceramics? No. There is a big difference between, let's say, covalent ceramics and ceramics with a high, large ionic fraction. So we can claim that ceramics with a large ionic fraction are very sensitive to slow crack growth. This is the case of all oxide ceramics, silica, zirconia, alumina, and so on. So all oxide ceramics have a large ionic ratio, and so a large tendency to water to absorb at the crack tip and act to help breakage of the ceramic bond. On the contrary, on the other side, covalent ceramics are almost not sensitive at all at ambient temperatures, of course, at ambient temperature to slow crack growth. I have plotted our own results obtained on different ceramics in a V versus K1 upon K1C values. So it's a normalized curve to have one for all the ceramics. So high crack rate for K1 upon K1C equal to 1. This is silicon carbide, silicon nitride. The slope is really steep. So there is crack propagation only when you reach a value which is very close to the toughness. On the contrary, this is mullite, an oxide ceramic. This is zirconia, and this is silica. The larger the ionic fraction, the larger the sensitivity of a ceramic to slow crack growth. You can see, for example, the ionic fraction of zirconia, 0.6. The ratio of K10 to K1C is about 50%. On the contrary, this is the case of silicon carbide, almost purely covalent. The ratio of K10 upon K1C is 0.9. So there is an effect of really the atomic structure at the crack tip. So we can imagine that there will be an effect of, for example, glassy phase. So we have processed different zirconia ceramics, white ZP, with silica at different locations. So here is a pure white ZP. As Thierry said this morning, the grain boundaries are very clean. There is no glassy phase, so we can model the microstructure like that. White ZP grains, another white ZP grains, no glassy phase at the grain boundaries. We had also some systems in which we have only glassy phase at triple points. So we can model the microstructure like that. Only glassy phase at triple points, not at grain boundaries. And for other silica plus alumina doped white ZP, we had this nice glassy phase at the grain boundaries. So the model structure was like that. And we tried to see if there was a difference in terms of crack propagation rates. So here is the undoped zirconia material, and doped only with silica. So we have this configuration with 0.5 or even 2.5%. You have an increase of the crack rate, but the threshold is the same. And that's quite obvious, since the crack has to propagate, of course, in the grain boundaries at the triple point. So you increase slightly the crack rate. But it has also, since it is an intergranular failure, it has to propagate in this region. So the threshold is not affected by a glassy phase at triple points. On the contrary, if there is some glassy phase in all the grain boundaries, then you can see it is the undoped zirconia ceramic, doped with silica. There is an increase of the crack rate and a decrease of the threshold. But just I want to say that zirconia is almost as sensitive as silica to slow crack growth. It's a highly sensitive to slow crack growth. So that's why we have an effect, but not so significant. Then comes the effect of the microstructures. So let's describe slow crack growth at the microscale level. We already described these reinforcement mechanisms, especially bridging, especially phase transformation. So let's talk about bridging. These are the three ceramics we have described before. 2 micron grain size, 5 micron grain size, 13 micron grain size. We have shown, especially Gilbert has shown, that the toughness was increasing with the crack length, and it was more important for 13 grain size than for 5, and then for 2. He called this the air curves. So the toughness is increasing with the crack length, slightly for the 2 micron grain size, larger for the 5 micron grain size, and still much larger for the 13 micron grain size. This should have an effect also on slow crack growth. So here are V versus K1 diagrams obtained on such ceramics. So this is the air curve, this is the slow crack growth. 2 micron grain size, 5 micron grain size, and 13 micron grain size. There is a clear effect of crack bridging on toughness, but also on the overall V versus K1 curve, on the overall crack propagation rates. And we can say that the larger the grain size, the larger is the slope of the V versus K1 diagram. And that's important, since this means an apparent lower effect of crack propagation, slow crack growth on the ceramic. Bridging is also effective in metal ceramic composites. So this is an example taken from our Spanish colleagues, Serafin Moya and co-workers. These are tungsten particles in alumina, and these are V versus K1 curves obtained for pure alumina. So you can see that the toughness is, even for that one, lower than 3 megapascal square meter. Here is the addition of 7% of metal particles, 10% of metal particles, 14%, 22%. So there is an improvement of the toughness by bridging by metal particles. And also, all the V versus K1 diagram goes towards the high K1 values. And also, you can see that the slope of the curve is more and more important. So here, you have a composite, a metal ceramic composite, for which the toughness and the threshold are quite the same, even if you have an alumina matrix, which is intrinsically sensitive to slow crack growth. But as we said during the discussion, you can improve the slow crack growth resistance to only a certain extent. Here is alumina ceramic with 6 micron grain size, 9 micron grain size, 35, so you increase the toughness, you increase the crack resistance, but past above a certain grain size, you have a strong increase of the toughness and the overall crack resistance. And this is due to the fact that for low grain size or moderate grain size, the crack propagation is intergranular, while for the other case, this is transgranular. So there is no more bridging to act to resist crack propagation. Here is toughening by transformation towards the monoclinic. So just few equations. Here is a notch and the crack propagating. You can see nicely the large transformation zone in a seria stabilized zirconia ceramic. And what we can calculate is the amount of shelding due to this transformation and the transformation zone. What we can calculate is that the transformation zone, so the transformation size, is a function of the applied K1. So the larger the K1, the larger is the size of this transformation zone. That's quite obvious, since large stresses means larger propensity of the ceramic towards transformation. And so the shelding, which is the stress intensity factor that acts to resist crack propagation, is a function of this process zone here. And so by combining these two equations, we can show that the shelding effect, so the toughening effect, is directly proportional to K1. So that's really interesting, since this means that the higher the applied stresses, the larger the reinforcement in a ceramic of that kind. So you apply a certain applied stress intensity factor, but in fact, due to phase transformation toughening, you have only a part which is used for crack propagation. So you have a shelding, and so the real stress intensity factor at the crack tip is lower than the applied one. And what is important is that we said that the shelding is proportional to K1. So again, combining these two equations, what we obtain is that the real stress intensity factor at the crack tip is only a proportion of the applied one. So if we take an intrinsic V versus K1 curve for a zirconia without any phase transformation toughening, so let's say something of that kind with a given slope, then the observed low is only shifted towards high K1 values. So here is the case of zirconia single crystal, low crack resistance, and here is the V versus K1 curve of 0.3 micron grain size zirconia, And here is the crack rate versus K1 curve of a 1 micron grain size zirconia. What you see is that there is a progressive shift towards high K1 values, but the curves are running parallel. So the effect of phase transformation toughening is to go towards the high K1 values, but preserving the V versus K1 curve of the matrix, of the intrinsic matrix itself. I didn't talk about compressive and residual stresses so far, and it's important for the following of the presentation. Especially in composites, you can have residual stresses since you have two faces. And so the residual stresses, especially if they are compressive in the matrix, can act to decrease the applied stress intensity factor. So again, you apply a given stress intensity factor, and then the real one at the crack tip is a function of the applied stresses minus the residual stresses. And what is important is that the effect of these residual stresses are much more important for low applied stresses. So the larger the applied stress, the lower is the effect of residual stresses. But what is important is that for low applied stresses, this effect is really, really important. So we have calculated for a given n value, n is the slope of the V versus K1 curve, without any residual stresses, what should be the value of n, so the slope of the V versus K1 curve, for compressive stresses in the matrix of 0 towards 800 megapascals. And what we show is that the higher the compressive stresses, the larger the n value. Of course, n value means, large n value means higher slope, so lower sensitivity to slope crack growth. So we can play also with residual stresses to act on V versus K1 curves. So let's go to the example for these two strategies for the 5 minutes which are still going. So I would like to talk about slope crack growth behavior of alumina zirconia composites, first with phase transformation toughening. That was our first, I would say, biocare approach. So it is currently used in orthopedy. So we have here an alumina ceramic and here zirconia particles. And the idea of such composites is that the crack is extending with time here. So the crack is propagating. And around the crack, the zirconia particles will transform. So you will have transformation toughening by the transformation of these zirconia particles. So we have an alumina matrix. The propagation is mainly in alumina. And we have zirconia particles, which means reinforcement. So here is the photograph of this kind of composite. I have forgotten to show these large defects sometimes appearing in this kind of material. And I take this picture. Here is the V versus K1 curve of alumina. K1C of alumina is about 4. The threshold is much below 3. Here is YTZP ceramic. Yttria stabilized zirconia ceramic. The toughness is here. The threshold is here. And so what about this ZTA with phase transformation toughening? We have 10 volume% of particles, which are transformable. And so we take the alumina, transformation toughening due to the transformation of this particle. We keep this curve, and it is just shifted to the high K1 region. But the slope is preserved, since we have the same intrinsic matrix. So you can see that the alumina has a low threshold, low toughness. And these alumina zirconia composites have larger threshold and toughness than alumina, and even with that of YTZP. And of importance is that the n value is that of the alumina matrix. And we know that alumina is by itself lower, less sensitive to slow crack growth, stress corrosion than zirconia. So here is the n of zirconia, quite low value, large sensitivity to slow crack growth. Here is the n value of alumina and the alumina zirconia composites, about the same, and we have larger values of n. And then the second approach, no transformation toughening at all in a zirconia toughened alumina ceramics. So it's an alumina zirconia nano-composite. And then we have in almost black, really gray, the alumina matrix. And you can see some small particles, some small dots, which are zirconia particles. They are so small that there is no phase transformation at all. Believe me, there is no phase transformation at all in the vicinity of a crack. So here are these zirconia nanoparticles inside the matrix. What about the V versus K1 curve? There is almost no bridging. There is, or few bridging. There is no phase transformation at all. What about the V versus K1 curve? Here is alumina, zirconia. Alumina, zirconia, standard microstructured composite. And there is the case of the alumina zirconia nano-composite, just with 2.5% of zirconia particles. You have an increase of the threshold as compared to alumina, but more important, you have a large improvement of the threshold as compared to alumina, or even better than that of alumina zirconia microcomposites. So how does it work? It works due to compressive stresses. We have measured inside the alumina matrix compressive stresses of about 150 megapascal. It can be 200 megapascal, frankly speaking, but some hundreds of megapascals in compression inside the matrix. The propagation is inside the alumina matrix, which is in compression. And so due to these compressive stresses, you act to improve, again, the toughness and the threshold. So playing with the micro or even the nanostructure of this nano-composite, you have a large improvement in the threshold. This is about twice than that of alumina. So this is finished for this second talk. So slow crack growth can be described in the framework as an extension of the Griffith approach. Slow crack growth is due especially to stress corrosion by water molecules. So there is an important role of the water. What is important also for design purpose is that there is a threshold below which no crack propagation occurs. So if we know the threshold, we can calculate the design based on these threshold values. At the atomic scale, slow crack growth is due to stress corrosion at the crack tip. There is an importance of the ionic to covalent bonding ratio, also important of the glassy phase. I said this is important, for example, since almost all the implants processed so far are based on oxide ceramics. And I see, for example, one interesting feature with covalent ceramics, since they are much more resistant to slow crack growth. At the micron scale, you can play a role with the microstructures by toughening, bridging, and also what is important with residual stresses. So I would say that V versus K1 curve can be tailored through microstructural control at different scales. And nanopowder engineering can be a power tool to, not powder, but power tool to improve slow crack growth resistance of ceramics. Thank you for your attention.